Assalamualaikum and good day. Today I'm going to represent my paper. Okay, the title for my paper is Artificial Neural Network Optimization in Prediction Baseline Energy Consumption to Quantify Energy Savings in Commercial Building. Okay, so these are my presentation outline, starting from introduction, problem statement, research objective, materials and methods, results and discussion, and last but not least is the conclusion. So we start with the introduction. Okay, so as we know, the population in Malaysia has increased substantially year by year. Okay, as reported by the Department of Statistics Malaysia, the gross domestic product GDP increased by 9.11% in year 2007 as compared to 2016 and estimated to increase throughout the year. Because of that, the residential and commercial sectors are also increased in parallel with this GDP growth. Okay, so demand of energy in the commercial and residential sector has increased, and this increasing trend is predicted to continue in the future. So, according to the Malaysia Energy Commission, the number of electricity consumers for commercial and residential buildings increased 2.7% from 2016 to 2017. So this contributes to the increase of electricity sales from 136,110 gigawatt hour in 2016 to 139,421 gigawatt hour in 2017. So electricity cost is the major contributor to the total buildings operating cost. Okay, so there is a need to reduce electricity cost and consumption while maintaining the productivity. So this situation has prompted Malaysian government to take several actions, including energy efficiency. So this energy efficiency of energy conservation measure or ECM has been introduced with the aim to reduce the energy consumption in the building. Okay, so measurement and verification or MNV is implemented to provide an accurate and consistent evaluation in determining the energy saving. So MNV actually is the procedure of using measurements to quantify savings produced in energy management programs. So actually there are several MNV protocols and guidelines established for determining and verify energy saving. But the most commonly used is International Performance Measurement and Verification Protocol or IPMVP. Okay, so basically this figure represents the MNV timeline. Okay, there are two different sections, the baseline period and also the post-retrofit performance period. Okay, so in between these two, the baseline and post-retrofit, there are the retrofitting program here. Okay, so in MNV, the development of a baseline energy model is important in order to determine the relationship between energy consumption and also independent variables. Okay, so to fairly compare the energy use before and after the ECM implementation, the variable condition in baseline and also in the post-retrofit must be similar to some extent. The baseline energy model was used to develop and estimate the adjusted baseline energy patterns, hence to quantify saving. Okay, so the adjusted baseline energy actually is the energy would have used if there had been no retrofitting implementation. Okay, so the adjusted baseline energy is represented by these red dotted lines here. Okay, so the adjusted baseline energy is then compared with the energy used in the post-retrofit, the blue lines here, to determine the saving. So as we can see here, the saving is the difference between the adjusted baseline and also the energy used in the post-retrofit base. Okay, so for the problem statement, recently the mathematical model using linear regression is the most common method used in formulating the baseline energy model. Okay, but the disadvantage is the linear regression is only suitable for the linear relationship and may contribute large error for non-linear data. Okay, so up to date, a little attention has been paid to the application of the ANN in developing the baseline energy model, hence to quantify the saving. But the application of ANN is more to the implementation of ANN based on the trial and error method. Okay, so based on the previous mentioned problem statement. So this is my research objective, which is to develop the option B IPMVP baseline energy model using ANN with several optimization techniques, namely evolutionary programming, particle swarm optimization, and also artificial bee colony, hence to quantify the energy savings in the post-retrofit period. Okay, so we go to the materials and methods. Okay, so for the data collection, okay, the data collection will gather from the chiller system of a commercial building in Kuala Lumpur using option B IPMVP data. Okay, so the real cases of this option B data were selected in this study to validate the effectiveness of this model. Okay, so for this data, three input variables that may influence the energy consumption were gathered, namely operating times, refrigerant tonnage, and also differential temperature. Meanwhile, the output variable is the hourly energy consumption. Okay, so the data were separated into two types, the baseline energy data and also the post-retrofit data. For the baseline energy data, 2928 hourly baseline energy consumption and independent variables were obtained from September 2015 to December 31st, 2015. Meanwhile, the post-retrofit data, there are 2184 hourly post-retrofit data from September 2016 to November 30, 2016. So for the model development, okay, there are two main phases in MNV energy model development. The first one is the baseline energy model and the second one is the saving calculation. The main idea of this proposed model is to optimize the ANN synaptic weight and biases to maximize the fitness. So the HANN optimization model were developed. Okay, there are three models were developed here, which is EPHANN, evolutionary programming hybrid with artificial neural network, PSOHANN, particle swarm optimization hybrid with artificial neural network, and also ABCHANN, artificial bee colony hybrid with artificial neural network model. Then the role of this ANN is to predict the energy consumption, and the optimization here is used to find the optimal synaptic weight and biases. Okay, so the coefficient of correlation, which is R, is used to find the strong correlation between targeted and predicted output. So the higher R represent the strong correlation between the targeted and predicted output. The other performance evaluation that also were used is the mean square error, MSE, standard error, SE, and also mean absolute percentage error, MAPE. So the lower value of MSE, SE, and MAPE show more accurate results. Okay, so based on this, the performance of these three HANN model will also compare with the ANN and linear regression to verify the proposed model. So in this model selection, the best baseline model with the higher R were then used in the second phase to calculate the saving. So the second phase is what we call the saving calculation. So in this saving calculation, the post-retrofit data, okay, here the post-retrofit data were loaded and applied to the ANN network, to the selected ANN network based on this model selection to determine the saving. Then in this saving calculation, the saving were obtained by compare the energy used and also the adjusted baseline in the post-retrofit data of post-retrofit phase. Materials and methods. Okay, so for the results and discussion, okay, there are two separate results. The first one is the result for the baseline energy model, and the second one is the result for the saving calculation phase. So in the baseline energy model, as represented here, the 16 model were construction for each techniques, and the total of 48 models were evaluated with different combination of neuron, as we can see here. Okay, so the model for EPHANN, PSOHANN, and ABCHANN. So as we can see here, among of these three HANN models, ABCHANN produce higher R than EPHANN and also PSOHANN in most of the neurons in the hidden layer. Okay, so the higher the value of R means that the better of the model performance. So the best performance of these three HANN model was selected and compared with the linear regression and also ANN method. See here, this is the performance comparison of this LR, ANN and these three hybrid ANN models. So as we can see here, the R for all models were higher than 0.95, means that this is acceptable by the IPM-BP. Okay, the results obtained indicate that all methods could be implemented for improving the model. However, as we can see here, the HANN model offers higher prediction result as compared to this LR and also ANN. So from here, we can see that the ABCHANN model achieved the highest performance. The ABCHANN model with 18 numbers of neurons in the hidden layer. Okay, so we will select this ABCHANN model as a best model and will be implemented in the next phase to calculate the saving. So this one is the result from the saving calculation. So we use the ABCHANN model to compute the adjusted baseline, hence to quantify the saving. So the energy saving obtained is 165,478.46 when we compare between this total energy consumption and also the adjusted total energy consumption for the baseline energy model. So this has contributed to 1.71% of energy saving in the baseline, which was equal to RM60,400 cost saving. Okay, so this calculation is based on tariff C1. Okay, medium voltage general commercial tariff calculation. And then the last one is the conclusion. So the paper was devoted to develop a proper baseline energy model to predict electrical energy consumption and to determine saving. Okay, so the baseline energy model has been developed with 3 input variables and the output is the energy consumption. So HANN with 3 optimization techniques were chosen. Okay, then were compared with the ANN and also linear regression. Okay, so the ABCHANN with 18 neurons perform well, and this model will be used in the post-retrofit to determine the saving. So for the future works, other IPMVP option with different data are proposed to assess the performance and the accuracy of the HANN model. So that's all for today. Thank you.